There we go. I think I was accidentally logged into another meeting and it wouldn't let me in y'all's. All right. Sorry about that. And I don't have the homework dates. I think 2.3 is due today. The 3.1, what did I set on that? Does anyone remember what day I had 3.1 due in my math lab? If you do, please say. Otherwise, it's set up in my math lab. You'll have it there for later. But the major thing I want to point out is that our second test. Someone said something. I believe it's the 30th. That sounds right. That sounds right based on everything I had going, because I had to do the lecture the 15th, but said I didn't force anyone to watch it till Saturday or yesterday on Monday, whatever you were comfortable with, and it was only an hour. So the 30th, that sounds right. So 3.1 is due on 6:30, and then the rest of the stuff we'll get as we go. But I want to point out the sections that are going to be on your second test, because they're a bit all over the place. The first test was chapter 1. It was pretty clear cut. This second test, because we're putting things together in kind of a piecemeal of sections, we're only going to have 2 sections from chapter 2. And then we're going to have 4 sections from chapter 3 for a total of 6 sections. Now, these problems on average, will be a little longer than the problems from the first test. So it's not necessarily going to be a 20-question test. The date is still going to be to be determined for now. But as I said, you'll get at least 1 week notice prior to the test. I will again give you a couple of days to complete the test. It is most likely going to be in my math lab again, with you submitting your work in Canvas like last time, in the instances of anybody needing a couple extra points, which I know one student pointed out, said, hey, I had this answer, I had a typo in my math lab, and I looked at their work and their work confirmed it, so they got full credit for the problem. So that was awesome. If you had any of those situations in the work that you've already turned in, and if you haven't turned in your work, it's too late at this point, but you can always let me know about those situations. So 3.1 is due on the 30th. We're going to finish 3.2 today, so that should also be due as well on the 30th. And then we'll have 3.4 and 3.6 to cover. I don't know that we'll finish 3.4. I've got a decent amount of word problems to cover in the next couple sections. So yeah, let's get it. So as a reminder of what we did last time in that hour lecture to make up for me having an appointment that I could not miss on Thursday, which I did not want to have to do. Believe me, that was not an option. So again, thank you all for your patience in dealing with this situation. But I'd say, at least, given that it's this online thing and everything's recorded, at least we didn't have to worry about a substitute or them doing something differently. I was able to just make it up later. So if you are a little behind, please make sure you don't miss that lecture, because everything we do today is kind of based off of it. So 3.1, we talked mainly about the first derivative test. And that first derivative test was used to find what we called local extrema, local maxima and local minima, the highest and lowest points of these little bumps, these hills and valleys. So the first derivative test was all about saying, all right, we find the first derivative. And the first derivative talks about how the function changes, how it increases and decreases. So after we find the first derivative, we set it equal to 0, because when it's 0, it's one of those peaks or valleys potentially. But it's only a peak if it goes from increasing to decreasing, and it's only a valley if it goes from decreasing to increasing. It is possible to see functions that increase and then increase. In particular, this point right here would have a slope of 0. Its derivative would be 0 at that point. It's increasing on the left and it's increasing on the right. So we have that 0 derivative, but it doesn't go from increasing to decreasing or vice versa, and that's why it's not a maximum or a minimum. It's just what we call a saddle point, which we don't really focus on in this course. So you can have zero derivatives that are not maxes or mins. The same can be said for the undefined ones, which we've also said deals with rational functions. That's 3.3, which will be what I'm calling a comeback section that we'll come back to at the end if we have time, which I don't anticipate. So we found where our derivatives were zero or undefined in theory. We find where it's increasing and decreasing, and anytime we see that increasing, decreasing pattern, we know it's a max. Every time we see that decreasing, increasing pattern, we know it's a min. In 3.2, we talked about the second, or we are talking about the second derivative test, but we haven't gotten to that yet. So far, we've mainly just talked about concavity. So concavity is related to the second derivative, and if your second derivative is positive, it means you're concave up. If your second derivative is negative, it means you're concave down. And this is what a section that's concave up or concave down looks like. It means you're bending up or bending down as you continue to move to the right. And then here's us saying what I just said out loud. If the second derivative is positive, concave up. If the second derivative is negative, it's concave down. Now, you're only finding this out at certain points. You're not saying it's concave up everywhere, concave down everywhere. It's possible, but a lot of these functions will be concave up in one region and concave down in another region, or concave up in several regions and concave down maybe nowhere potentially. That is possible. It's weird, but it's possible. So when you're in a region that looks concave up, you're shaped like this. When you're in a region that's concave down, you're shaped like this. So what the second derivative test is centered around is that you find your critical numbers. You find where your first derivative is zero. So if you find where your first derivative is zero, it's likely this point or this point. It's very likely to be one of these points. So what you then do is you go to the second derivative and you actually plug in the critical number. And if that critical number is positive on the second derivative, it's concave up, which means that point has to be a min. Or if the second derivative of a critical number is negative, that means we're here, and it has to be a max. So the second derivative is similar to the first derivative test, but it also is a little different. The first derivative test, we were plugging test points in. In the second derivative test, we're actually going to plug the critical numbers in, because all around that critical number, the concavity should be the same in that local region. So you don't have to do test points. And in fact, if you take a test point too far out, that test point doesn't prove anything necessarily. So that's the main difference between the first and second derivative test. Instead of plugging in test points, you're plugging in the critical numbers, but into the second derivative. You're not going to plug them into the first derivative because you know it'll spit out zero. So the other thing we talked about was inflection points. This is where the concavity changed. We showed what that tends to look like. And we found inflection points and where it was concave up and concave down by doing a test point approach on the second derivative. That's not what I was just describing a few minutes ago. So when you're checking concavity or when you're trying to find inflection points, this is the same as the first derivative test, but under the second derivative test. But under the second derivative, excuse me. You do have test points to find concavity. But when you want to do the second derivative to find maxes and mins, you use the critical number instead. So that's the major difference there. And you've got to make sure you're practicing on your homeworks, because if you don't practice, when you get your test, you're likely to do the test points instead of the critical numbers or vice versa under the second derivative. Now, all the things I said earlier, I'm of course going to write on the screen right now. So here is our second derivative test. So first, find the first derivative. And then set it equal to 0 and or undefined if you've got a non-polynomial function. Find its critical numbers. Then, there we go. Second, we find the second derivative. Then you will plug in the critical numbers, not test points, not test points, not test points. You will actually plug in the critical numbers into the second derivative. If you plug it into the first, you're going to get 0 or undefined every time. It's not going to tell you anything. If this value is positive, it means the function is concave up in that region, and thus a local min. Not enter, there we go. If this value is negative, it means the function is concave down in that region, and thus a local max. Again, the picture says 1,000 words. You find your first derivative, then you find your critical numbers. At the critical numbers, those are potential extrema. Then you find the second derivative. So if you have a point, here's your critical number. Now you know at this critical number, if it's a max or a min, it's going to look like this, or it's going to look like that, one or the other. It either has to be going down, or it has to be going up if it's an extrema. Like I said, it's possible they go in different directions, but if it's an extrema, that's what happens. That's what we anticipate. So we know that would happen at the critical number potentially. When we go to the second derivative, we just plug this in to find its concavity. So if we plug the critical number in and we get 7, that means the function is concave up around the critical number. Well, a critical number has the 0 derivative, which means it has to look like this. If you're concave up at the critical number, it has to look like this so that your tangent line is horizontal. Well, if you're concave up, that means it has to be a min. Conversely, if you plug the critical number into the second derivative and you get, say, -5, that means you're concave down at the critical number. But the only way to be concave down on a critical number is to look like this. That way its tangent line is, again, 0 slope. It's horizontal. So if we're concave down around a critical number, that means it has to be a max. This feels backwards. I know it feels backwards because you get, if you plug it in and you get a positive value, it's a min, and a negative value, it's a max. That feels backwards. Guess what? In math, a lot of things feel backwards. We dealt with that a lot when we were shifting and reflecting graphs back in pre-calculus. We dealt with that a lot when we were trying to deal with the vertices of a parabola back in pre-calculus, like that x minus h scenario. Now, on a test, on an actual test, if the problem says to use the first derivative test, your work needs to show the first derivative test. If the problem says use the second derivative test, you get the idea, your work should show the second derivative test. If you get the answer right on a test, and then I go back and look at your work, and you don't follow the instructions they request, I reserve the right to dock some or all of your points. And admittedly, I won't dock all, it would be some. I think at worst, I'd give you half credit, and I'd probably even be a little more generous than that. But following instructions is important. Now, I am 99% of the time all about if you can get an answer right every time, why does it matter how you got the answer as long as it's consistent? The reason I say that for these is, first of all, some of the problems where they ask you to use the first derivative test, if you go to the second derivative test, it could be inconclusive, or it could be really, really, really hard. And some of the problems that are supposed to use the second derivative test, once again, it could be, I don't want to say it would be more difficult to use the first derivative test. That's pretty rare, but it could be a bigger pain in the butt. It could be more time consuming. There are times when the first derivative test is better. There are times when the second derivative test is better. And how do you know when they're better? By practice. I could tell you when it's better. Certain types of polynomials, it's better just to do the first derivative test. or the second derivative test. If you've got a product or a quotient, the first derivative test is probably easier because if you got to take a second derivative of a quotient, that's 2 quotient rules. Doesn't sound like a good idea to me. Same for a product. But if it's a straight up polynomial, first derivative test is usually fine. But again, there are times when a second derivative test can be inconclusive. There are times when a first derivative test can be inconclusive. So you need to follow given instructions. Once again, I reserve the right to take away points if you don't follow instructions with this. I didn't really do any of that in test 1. I can't really think of a scenario in test 3 where that will be the case, but you must in this instance. All right, rant aside, which I know we all love Mr. Beckner's rants, let's try this out. Example 1. So we are going to find all relative extrema by the second derivative test. And we'll have the function x cubed plus 3x squared plus 3x plus 6. That's our original function. So we want to find the local extrema. We want to find the highs and the lows in local or relative areas. So we got to find the first derivative. 3x squared plus 6x plus 3. Okay, so we take this and we set it equal to 0 to find the critical numbers. If this was a fraction, we'd set the top and bottom equal to 0 to find critical numbers. So we go 0 equals 3x squared plus 6x plus 3. And we got a factor. Pop a 3 out as a GCF. You get x squared plus 2x plus 1. Factor pairs of 1 that multiply to 1 but add to 2 are 1 and 1. So we go 0 equals 3 parentheses x1, x1. And all these are positives, so all these are positives. Again, 10 million times I've said it, you've got to know how to factor. Now the x plus 1 and x plus 1 are the same, so they're not going to lead to different answers. I'll show all 3 equations, but you get 3 equals 0, which is trash. We've seen something like that before. Throw it away. We get x plus 1 equals 0 and x plus 1 equals 0. Subtract 1 on both of those and you get x equals negative 1. 2 times. Those are our critical numbers. Well, critical number singular since we only found 1 twice. Now, when we talk about the multiplicity of a 0 in a regular function, that talked about whether it bounced or crossed, so it gave something unique. Maybe when a critical number repeats, maybe that has something to do potentially, and I'm not going to say explicitly, but maybe that has something to do with extrema as well. I don't want to spoil too much though. So if this was the first derivative test, we only have the negative 1 up there. We draw a negative 1. So again, I'm going to write some stuff up and then erase it. If this was the first derivative test, we have our number line with the negative 1 as our critical number, and then we'd use negative 2 as a test point, and we'd use 0 as a test point. But we're not doing the first derivative test for now. We were told to do the second derivative test. So what that means is we need to erase all that. There we go. And we're supposed to take the second derivative. Once we have our critical numbers, take the second derivative. Hold on a second. What's going on? Okay, sorry about that. So now let's take the second derivative. I'll do that in blue. So f double prime of x. So let's go back to before it was factored, because why would you want to use a product rule if you have a version where you don't have to use the product rule? So we'll take the 2 out in front, so that'll be a 6x. The derivative of a plus 6x is just a plus 6, and the derivative of 3 is 0. I'm going to say this again. You have got to be the kings and queens of your power rules. You need to know your product rules and your quotient rules inside out as well as your exponential and log rules. But the power rule is the one you see the most. You cannot pass this class without your power rules. A student could arguably pass not knowing maybe one of those other things. You need to know some. You can miss one and still pass with like a B or a C, but you ain't gonna get an A. Okay, now if we were finding concavity, we would set this equal to 0. So I'm just gonna go back to it for a second, just as a reminder. If we were talking about concavity, just concavity, not extrema. We were just talking about concavity. That's where we set the derivative 0 and then did the test points around it. That's not what's happening here. I did not ask for concavity. So I'm not setting this equal to 0. We now plug the critical numbers into f double prime to see how the concavity is at those numbers. So we'll do f double prime of -1, which is 6 times -1 plus 6, which is -6 plus 6, which is 0. What? So that means it's not concave up or down at the critical number. What this means is inconclusive. Well, that sucks. I just told you to do a problem by the second derivative test and I came up with something that was inconclusive. I bet you I did that intentionally. I bet that has to do with the thing I was saying earlier about your test problems where if it says to do it one way, you should do it that way. Okay. So if this is inconclusive, what you should do is try the other test. Since the second derivative test was inconclusive, try the first derivative test. So that thing I had earlier in black, that's what we're going to do. And we're going back to the first derivative, so I'll do it in red. Okay, so we have our number line. Well, yeah, number line. The only critical number we had was the -1, so that's our critical number. We'll use the -2 as a test point and the 0 as a test point. So we're going to do f prime of -2. Remember, it's easiest to plug it into a factored form if you have it, and just do the signs. So 3 times -2 plus 1 times -2 plus 1, which is a positive, times a negative times a negative, which is a positive. So that says it's not concave up. Remember, second derivatives, concavity. First derivatives, increasing or decreasing. That says it is increasing in the region of the -2. So in the region of the -2, it's going up until we hit the critical number. Now let's try what happens to the right of the critical number. So f prime of 0. That's 3 times 0 plus 1 times 0 plus 1, which is a positive times a positive times a positive, which is a positive, and it's increasing again. We have not seen that happen yet. So in the region to the right of the -1, it's going up again. So I feel like we tend to draw it that way, so maybe keep drawing it that way. And if that's a little weird to you, instead of having it disconnected, let's do it this way. So we're going up until we hit the -1. So here's the -1. And then we're going up again. And it probably doesn't do that. It probably bends the other way. And I say probably because it's possible that it bends the other way, but this is increasing on the left, and then this is increasing on the right. This is not a max. This is not a min. This is what's known as a saddle point. A saddle point is a critical number that is not an extrema. it's saddled between two different sections of being increasing. So this problem has no extrema. If you don't believe me, graphing calculator. Go to the graph screen. What was our original function? X cubed plus 3x squared plus 3x plus 6. Go to graph. And look at that. Here's our -1 if I hit trace. -1. There's the critical number. You can see that the derivative is 0 there because a tangent line would be horizontal. Let me zoom in on that point just to make that a little more clear. Look at that. So we're increasing, we flatten out to 0, but then instead of turning back around, it has more of a cubic function look and it keeps on increasing. This is possible. And guess what? This has everything to do with the fact that there's a multiplicity in the critical numbers and that the multiplicity is even. So this is what a saddle point looks like. It's when we go increasing and then increasing, or vice versa, decreasing and then decreasing again. So it's not a max, it's not a min. It's neither. So there were no extrema of this problem. Now, very often, when you see the scenario, the second derivative test is going to fail because the concavity here is 0. Because if you look left, let me throw the annotate on and just kind of draw over my calculator. To the left, if you kind of ignore what's happening here, this is concave down, so you'd think it would keep doing that, but then to the right, it's concave up. So we are actually switching concavities there immediately from down to up. Those parts just don't exist. So we went from concave down to 0 concavity and then concave up. So because the concavity was 0 at that point, you can't tell whether it's facing up or down. And that's because it was neither. It's kind of like joining both of them together. I'm gonna have a hard time finding that problem because I didn't grab the page. Let me just do this. This will be easier. So what you might think is that the second derivative test is bogus. Let's actually pull a problem we've done before. Which will be this one, this x cubed plus 12x squared minus 60x, et cetera, et cetera. So for example 2, oops, wrong color. And whoa, 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 whoa. I hate when I scroll over that thing. Let's just go ahead and bump this down. So same instructions. Find extrema by the second derivative test. And this function will be x cubed minus 12x squared minus 60x plus 36. So we're going to go through and take the first derivative. F prime of x equals 3x squared minus 24x minus 60. I am not going to spend a lot of time doing this since it's already been in another section. You set it equal to 0. I could have just copy pasted it. You factor, you get 0 equals 3 parentheses, and it's originally x squared minus 8x minus 20. Then you'll get 0 equals 3 times factors 10 and 2. Yeah, 2 and 10. Make sure they add to a negative, so the 10's negative, the 2's positive. When you set each of those equal to 0, the first will be trash. You get 0 equals x plus 2, and 0 equals x minus 10, so x equals negative 2, and x equals positive 10. Those were our critical numbers. Again, because I'd already done that work, I could just borrow it, but because I'm trying to do something else, ultimately, I wanted to re-show the work. Now we find our second derivative. Let's go back to this version. This is easiest to find the second derivative on. So bring the 2 out front. That's a 6 now. 2 times 3, decrease the exponent by 1. The derivative of negative 24x is negative 24. The derivative of negative 60 is 0. All straight power rules. Now, if I asked you what's the concavity in the different regions, are there any inflection points, all that jazz, that's when you set this equal to 0 and do that test point stuff in the second derivative. That's not what we're doing here. All we do is plug in the critical numbers. So we'll do f double prime of negative 2, which is 6 times negative 2 minus 24, which is negative 12 minus 24, which is negative 36. All that matters is that it's negative. If it's negative, that means it's concave down in that region. So in that region, it has to look like this. In the region of the negative 2, this is what it looks like. But we said that our derivative is 0, the first derivative specifically, at the negative 2. So therefore, based on this picture, it must be a max. Again, because when we plug the critical number into the second derivative, the thing that talks about concavity, because it came out to a negative value, last time it came out to 0. Last time it came out to 0, which is inconclusive. We need it to be a positive or negative number to be able to tell what's happening. So because it's negative, now I don't need to know what happens around it. It's negative at this region, so it looks like this, and the critical number has to be the highest or lowest point because of the whole theory. Therefore, it's a relative max based on that picture. It's not just a straight blatant memorization of if this value is positive, it means it's concave up, which means it's a local min. Yes, you can straight memorize that if you like, but I usually like the pictures 1,000 words argument. But you do you. What is the max? So we got to plug it in. We got to plug in the negative 2 to the original function. So we do f of negative 2. I'm going back to black because we're back in the regular function. So that's negative 2 cubed minus 12 times negative 2 squared minus 60 times negative 2 plus 36. And we already have that answer from before, or at least we should. That was the one that I had goofed it incorrectly at first. That was 100. So now let's go back to the second derivative. But now we're going to plug in the other critical number, which is 10. See, we're only plugging in the critical numbers into the second derivative. So the second derivative, that's the 6x minus 24. So 6 times 10 minus 24. It's a times and a minus, which is 60 minus 24, which is 36. That's positive, so therefore it's concave up in that region. So in the region of the 10, it has to look like this. It has to be concave up. But we know the 10 is a critical number, which means it has to be this. This has to be the 10, which is the lowest point in that region. Therefore, it's a relative or local min at x equals 10. But again, what is it? Go back to the original function, f of 10. That's the 10 cubed minus 12 times 10 squared minus 60 times 10 plus 36. And that's that 764 number. Let me make sure it was 764. Yes, negative 764. And then you could graph it from there. I didn't ask you to graph it because we already did that. But once you have your extrema, if I asked you to graph it, which is a possibility, oops, wrong thing. You can plot that -2, 100, the 10, -764, and then you just bend around your polynomial shapes like you know to. At a max, you're going down around the ends. At a min, you're going up around the ends. And then you just connect in a smooth, like polynomial fashion. All right, let's do one more of these. And I might be able to get it all on this one. Let me go to a new page just to be safe. Same instructions, example 3, and this function will be x to the 4th minus 8x to the 3rd plus 18x squared plus 2. So find the first derivative. Which is 4x to the 3rd minus, bring the 3 out and multiply by the 8, which is 24. Decrease the exponent by 1. Bring the 2 out and multiply by the 18. 2 times 18 is 36. Decrease the exponent by 1. And the derivative of 2 is 0. We will then set it equal to 0 to find the critical numbers. So we go 0 equals 4x cubed minus 24x squared plus 36x. And then we factor. There's a GCF to take out. And that GCF, 4, 24, and 36, 4 can go into all of those. You got x cubed, x squared, and x. So you can actually take an x out of these. That's something we haven't seen in this chapter, but it's something you should have seen 5,000 times before today. Dividing all these by 4x, you'll get x squared minus 6x plus 9. Keep factoring. The factor pairs of 9 that add to 6 are 3 and 3. So we go 0 equals 4x times x3, x3, but you gotta give them signs. To make sure they add to a -6, they both need to be negative. Ooh, look at this. We got a repeated 0. I bet you that this is going to lead to an inconclusive second derivative test for that one. But I bet we can still make the analysis on this one because this one isn't repeated. And you might say, well, this is the garbage part, this 4x. Hold that thought. So let's make our equations. 0 equals 4x, 0 equals x minus 3, and 0 equals x minus 3. Setting each of those equal to 0, for the first one, we divide both sides by 4. It's not garbage, there's an x there. And you end up with 0 equals x. So there is actually a critical number there. Add 3, and you get x equals 3. So our critical numbers are 0 and 3. That's not a point, those are two different x values, and I want to label that more specifically. X equals 0 and 3. Those are the two possible maxes or mins. It could be both are maxes, it could be both are mins, it could be one max, one min, or they could both be saddle points, or one of them could be a saddle point and the other is a max or a min. These are all possible scenarios. Now, we said to use the second derivative test. Now, we could also say, well, maybe it didn't say use the second derivative test, maybe that's just what we want to do. And quite honestly, for most problems, specifically with problems that don't have this thing going on, the second derivative test is quicker for a regular polynomial if you don't use a product rule, if you don't need a quotient rule, because you're only plugging in critical numbers instead of test points, and there's always one less critical number than test points. So if there's two critical numbers, that means you'd need 3 test points under the first derivative test, but only 2 plugins under the second derivative test. All right, so again, let's not use the factored version. Let's use the polynomial version, the 4x cubed part. So taking that derivative, 3 in front of the 4, that's 12. drop the exponent by 1 to a 2, minus 2 times 24 is 48, drop the exponent by 1, plus, this is a linear term, the derivative of a linear term is just the constant coefficient, it's plus 36. Again, I'm not asking what the concavity is, I'm asking what the extrema are. So we just plug in the critical numbers. So f double prime of 0 is 12 times 0. And you could factor this if you wanted to. It might factor easy. It might not factor at all. I'm just going to go straight up this way. Minus the 48 times 0 plus 36. All the first bits cancel. You're just left with the 36. That's not 0, so there's a conclusion. This is positive, so concave up. If it's concave up at a critical number, this is what concave up looks like. So we look like this in that region, but the critical number has to specifically be this point. So that's 0. So that means it has to be a relative min at x equals 0. And if you want to find out what that relative min is, you plug it into the regular function. So we do f of 0, which is 0 to the 4th minus 8 times 0 to the 3rd plus 18 times 0 squared plus 2. All the beginning part is just 0. The only thing you're left with at the end is the 2. So the point is 0, 2. The relative max, I'm sorry, excuse me. The relative min is 2, and it occurs at x equals 0. Remember, the phrasing is very specific. And I didn't say the phrasing last time, so I will this time. The relative min is 2 and occurs at x equals 0. Now, there can be more than one relative minimum, so I may need to switch my phrasing to a relative min is 2 and occurs at 0. Okay, well, what about the 3? So let's do f of 3. So that is 3 to the 4th power minus 8 times 3 to the 3rd power plus 18 times 3 squared plus 2. And let's just pull out a calculator for that annoying jazz. It's not the end of the world to do by hand, but let's save ourselves some time. So 3 to the 4th minus 8 times 3 to the 3rd plus 18 times 3 squared plus 2. And we get not the number I wanted. Why did I plug it in the regular function? I'm sorry. Why would I be this is a whole ask yourself, does it make sense? I'm supposed to be checking the concavity, right? For some reason, because I had just plugged it into a function here, I did it again. So that was a mistake on my part, but I caught myself. And it wasn't a fake mistake. I do fake mistakes sometimes, but that was completely wrong. So let's erase that. Remember, this would give you the function value. So the function value is 29, but that doesn't tell us whether it's a max or a min. We're supposed to be going back to the second derivative. And we're plugging in 3. So that's 12 times 3 squared minus 48 times 3 plus 36. All right, sorry about that. But I do like when that happens because I hope that you learn from that and learn to ask those questions yourself. So 12 times 3 squared minus 48 times 3 plus 36. And that's the answer I expected because of the repeating critical number. We get 0. If it's positive, it's concave up. If it's negative, it's concave down. If it's 0, it's inconclusive. It's possible it's a saddle point, but it's possible that something else is going on. So what you have to do is go back to the first derivative test. Now we already have the information about 0, so we don't have to set up everything. We just need to set up around the 3. So into the first derivative test, we're only worried about x equals 3 as a critical number. So when I draw this up and I put my 3 up here as my critical number, the 0 is over here also, but I don't care about it. I don't need to check to the left of it. So I'm gonna put a little asterisk above it and just say, there it is, because I also want to make sure I don't go too far. So when I do my test points, they still have to be to the right of the critical number and to the left of it, but I can't use 0 because it's a critical number. I can't use -1 because it's to the left of a whole nother critical number. It has to be between 0 and 3. So the only good whole numbers are 1 or 2. Let's go with 2. So now we can plug the 2 and the 4 into the first derivative. So f prime of 2 would be 4 times 2, then times 2 minus 3 times 2 minus 3. 4 times 2 is 8, which is positive. 2 minus 3 is -1, so negative, negative, and that's a positive. So it's increasing. In the region of the 2, it's increasing. I'll do this as straight lines this time instead of the curves. Now let's do the 4. So that's 4 times 4, and then times 4 minus 3 times 4 minus 3, which are all positive, which means it's increasing again. So to the right of the 3, it's also going up. So this is a problem. It's increasing, it hits its 0 derivative, and then it starts increasing again. So this is the most likely appearance around the 3, which means it's again a saddle point, not a max or a min. So there's only one extrema. And that was the relative min of 2 at x equals 0. I could give you a problem with 17 critical numbers and there's only one extrema. I can give you a problem with one critical number and there's no extrema. I can give you a problem with 17 critical numbers and there's 17 extrema. Anything is possible. So if I asked you to graph, I didn't ask to graph, but if I asked for it. So we have the relative extrema at 0, 2. There's a height of 2. And that's supposed to be a relative min. So in that area, it's supposed to look like that. Then we have that other point, and you did see the math earlier. What was that output? Was it 29? Let me put my calculator back up. Just recalling some functions with second enter. This was me plugging in the 3 to the real function, and it was 29. So just note f of 3 is equal to 29. So over here, 1, 2, 3, there's a point way up here at 29. This is going to be a little skewed. So here's my 329. So we know we're bending up around the relative extrema. We know we're going to be increasing until we hit that point. But when we hit a critical number, they tend to flatten out. But then it keeps increasing, so it would go up again like that. I'm going to redraw this graph lower. That's not enough space. Let's just say here's our height of 2 and here's our height of 29. So here's the 0, 2. Here's the 1, 2, 3, comma 29. Those were our critical numbers, so we know the derivatives are 0. We know this was a relative min, so it had to go up around both. But we're going to go up, 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 up. Let's start flattening out as we get a little closer to the critical number. You can just barely see it, but I'm flattening out. But then we said we were increasing again on the right of it, so we keep going up. And again, this little bump is not perfect. The left side, there's nothing to tell us to turn around. There's no relative extrema. Those are our typical turning points. So we just keep going up and up and up and up and up like this. And again, this little region right here just looks a little goofy. It's not super smooth. It should look more like this. That's more what it should look like in that region. Just to be a little better. The circle, I'm not drawing a yin and yang. I'm just saying this is me blowing up that region and making it look a little better. So maybe you don't trust this. Graphing calculator, go to your y equals screen. That is the other one. We are dealing with 4x, sorry, x to the fourth. X to the fourth minus 8x to the third plus 18x squared plus 2 okay. So here's our 0, 2 min, and that's all we can see because this has a height of 10 and negative 10. So let's change the window. We need to at least have a height of 29. Let's make it like 40. So I go to window, y maximum, and make that a 40. I'm only going between 0 and 3 really on the x-axis. And look at that. Look at that. That's pretty good. Like I said, it should be flattening a little more. It's just, I'm already a not great artist. You throw me a pen that I can't even watch myself draw, and things like that happen when I'm trying to have it zoomed out. But there we go. We can see that we have our min here. We can see that this is a critical number because the derivative is certainly 0 here. A tangent line would certainly be 0, have it be horizontal and have a 0 slope there. But it doesn't turn back around. It keeps trucking in the same direction, which is why it's not a max or a min. It's not an extrema. So that's one of my favorite problems from this section because it has both the issue of the second derivative test being inconclusive as well as a critical number that you could actually determine with the second derivative test. Again, I like the second derivative test when it can be used easily. If it's a power, if it's a power rule, I typically go to the second derivative. If it's a product or a quotient rule, I'm going to stick with the first derivative because taking those derivatives is more time consuming, especially the quotient rule. If it's an exponential, I think it's pretty fine either way, whether you use a first or second derivative test if it's your choice. And some problems I would give you the choice, some I won't. When it comes test time. Okay, so as a reminder, I was worried that graph was going to get messed up. As a reminder, an inflection point is where a function changes concavity. It changes from concave up to down or from down to up. It can't be concave up, then 0, then concave up, or down, and then 0, and then down. So it's where a function changes concavity. It goes from positive to 0 to negative, or negative to 0 to positive, one or the other. In economics, this is the point of what we call diminishing returns. Diminishing returns is the act of still gaining more of something as you move on, as you or time or whatever or as you, let me phrase this a little nicer. As, I don't want to just say as the input variable goes on or as it increases, because that's kind of weak. Let's say as time goes on or production goes up, things like that. So diminishing returns is the act of still gaining more of something, more money, more satisfaction, more something. But the rate at which you're gaining more is decreasing. So maybe day one, you gain 15 items. Let's say $15. Day two, you gain $12. Day three, you gain $10. Day four, you gain $7. Day five, you gain $4. Day six, you gain $3.50. From the Loch Ness Monster. Sorry, terrible joke. Old joke. Maybe one of you gets it. This is diminishing returns. So when I say gain, I mean profit, income, whatever. You're gaining more the next day, you're gaining more as time goes on, but your gains are decreasing. So this is the idea of diminishing returns. We still gain each day, but our gains are slowly decreasing. Oh, that's going to screw it up. Let's just use, and you get the idea. There we go. Word is fun sometimes. I also liken this to the Dorito problem. You open the half a pound bag of Doritos or 10-ounce bag of Doritos, however big it is now. It used to be a pound, and then they made it 14 ounce, then they make it 12 ounces, and they never change the price. They just give you less and less chips. This is also true of ice cream. Ice cream containers used to be bigger, and to keep them the same price, they just make them smaller. And they expect most Americans not to realize it, and most of them don't. So you're paying the same price, but you're getting less. You're like, man, that ice cream container went quicker. That bag of Doritos went quicker. What's going on? Is it me? Am I eating more? No, it's just a company hiding them, upcharging you because of inflation and such and greed. A little of both. So the Dorito problem, you open your 10 ounces of Doritos and that you're hungry, and that's the air just fills with that salty scent, and you eat that first one and it's glorious. It's the best chip you've ever had, right? And then you eat the second one and it's still amazing, and the third one's amazing, and the fourth one's amazing. And then you eat your 12 or 13 chips, whatever a serving is supposed to be. But we're Americans, so we don't eat just one serving. We have some more. We have our 13th chip. But I tell you what, you're still happy with that 13th chip. You're happy because you're still eating it. You're gaining some satisfaction. It's filling your belly. Your taste buds are still firing off. But it's not as good as that first chip, is it? That first chip was like a miracle. The 13th one, it's great. It's great. That's not bad. Great's good, but it's not a miracle. And then you eat your second serving, and then you're on your 25th chip. And now you're like, I mean, I can keep going. They're still tasty. I don't necessarily need to keep eating, so I'm going to keep doing it. That 25th chip isn't as good. And then you eat your third serving and your 36th chip. I mean, it's fine. It's okay. Why am I doing this to myself? But you keep doing it. You must be getting something positive out of it. But the amount of that positive is slowly and slowly shrinking. Now, diminishing returns can lead to negative output ultimately, or it could just be slowly going to zero gains. So maybe day 1 million, we're gaining 15 cents, something like that. And that's when we have asymptotic behavior, like in 3.4, which is it 3.3? 3.3, excuse me, that we'll hopefully get to circle back around to. All right, so I have an example. What example number are we up to? 4? Yes. Got a nice word problem. A company predicts if it invests X $100,000 in advertising, its revenue will be color 30x squared minus 2x cubed plus 100 in hundreds of thousands of dollars. That's a terrible looking zero. I don't know what was going on with my pen there. I've kind of figured out how to use the erase button, but I'm still working on it. Anyways, in hundreds of thousands of dollars. This is only going to be for X between 0 and 9. That's called a constraint. Constraints are very important for realistic models because the models that we make tend to be oversimplified and only good on a short scale. So if you go past 9, maybe this model is no longer accurate. Population dynamics, if we want to describe the population as linear growth, that's only good for like 10 years, maybe 30 years. If you want to talk about population growth as an exponential curve, it's good for maybe 50 to 100 years. But if you want to talk about a population dynamic over thousands of years, you have to go to that logistical curve that I've mentioned in passing, where you see the explosion for a while, but eventually we slow down due to constraints, due to reasons that will start capping our population, whether it be the size of our planet, the amount of resources we have, whatever. Find the point, back to the question at hand, find the point of diminishing returns. In other words, when the company will still make more money if it makes more items, but the more money part is going to get smaller and smaller. So, all right, if you make 8 items, you'll make $100 more in profit, whereas if you make 9 items, you might only make $80 more in profit. Well, you still want that $80 more, but you just need to understand that you're not going to be collecting money as efficiently. It's not necessarily bad, but maybe it is. It depends on your company. All right, so what were we saying about diminishing returns? What does it have to do with? It's an inflection point. So in economics, the point of diminishing returns is the inflection point, which means ultimately we need to find the first and second derivatives. So we'll do f prime of x, which is, and note that this is a funny ordered polynomial. I chose this one intentionally because the middle term is actually the guiding term because that's the one with the largest exponent. Do you have to reorder this? No, it might be helpful. Let's just pause on that and see if we can leave it all in for now. Bring the 2 out front, that would be a 60, decrease the exponent by 1, so 60x, minus, bring the 3 out front and multiply, so that's a 6, 3 times 2, decrease the exponent by 1, the derivative of 100 is 0. So there's our first derivative. I didn't say find local extrema, I didn't say find maxes or mins, so I'm not going to set this equal to 0. I'm going straight to the second derivative. The derivative of 60x is 60, minus, drop the 2 out front, so that's a 12, decrease the exponent by 1. So our second derivative is 60 minus 12x. Now we're supposed to be finding the inflection points. Inflection points are where the second derivative is 0 and it changes around it. So we set this equal to 0. So we go 0 equals 60 minus 12x. You can add 60 to, subtract 60 to both sides or add 12x to both sides. I'm going to add the 12x just to go ahead and get the positives. If you subtract 60, that just means your next step is to divide by negative 12 instead of us dividing by the positive 12. Ooh. There we go. Give me the black, please. Thank you. Divide by 12. and 60 divided by 12 is 5. So we get x equals 5. This is our potential inflection point. Potential inflection point. To know whether it is the inflection point or not, you have to, on the second derivative, test around it, find the concavity around it, and make sure it changes concavity. So we got to do test points. 4 and 6 would be great test points. Or 0 and 6 if you want to do 0, because 0 is always an easy number to plug in. We plug these into the second derivative because we're checking concavity. So f double prime of 4. That's 60 minus 12 times 4, which is 60 minus 48, which is 12. That's positive. By the way, if you want to write that extra detail, you can write that's greater than 0. So it's concave up, which means in the region of the 4, it looks like, I'm going to draw it above, it looks like this until you hit the 5. So there's your 5. It's concave up in that region. Now again, we didn't plug a critical number in. Our point's not here. The 5 is over here. The 5 is not a critical number. I have some random number to the side where it's still concave up. Now let's do the 6. F double prime of 6, which is 60 minus 12 times 6, which is 60 minus 72, which is negative 12. That's negative. If it's negative, it's concave down. Which means in the region of the 6, it's concave down. And again, that's not a critical number, so the 5 is supposed to be over there. So we go from concave up to concave down. It's switched, so it is an inflection point. So since concavity switched around x equals 5, x equals 5 is an inflection point, thus the point of diminishing returns. Now, this function was a revenue function based on how much they spend on advertising. It's kind of a weird, atypical function. Usually revenue functions are based off of quantity of items produced, but this is talking about advertising, and in advertising you spend money to make money. So advertising, the input and the output is both money. If you spend $100,000, maybe you'll take in $1 million. Whereas non-advertising revenue functions are based on, well, if you sell this many items, you'll take in this much money. So advertising doesn't have anything to do with the number of items. It has to do with how much you spend and how well you advertise. Now, this function, X, was represented in hundreds of thousands of dollars. So that 5 is really $500,000. So when the company spends more than $500,000, can still expect to bring in more revenue, but that revenue increase is slowly decreasing. So let's pull out our calculator to make this simple. And I want to show you a trick you can use with the TI-83. And you don't have to do it this way, but I'm just going to type the function 30. I'm actually going to use x. Here's my x button. 30x squared minus 2x to the third plus 100. I can actually store values of the x in this calculator. See, it just spit out a number. How did it get that? If I just type x, my calculator right now thinks x is 10. So if we spent $100,000, in other words, $1 million, we could expect to have this as our output again in hundreds of thousands of dollars. So that's a large amount of revenue. If our x is 5, So let me show you that's 5, then the store button, and then X. And if you don't want to do this, you can just go back and type in the numbers and do the math. So now I'm telling my X is 5. So if I hit X, that's 5. So I can now recall that original function. Just takes a few times because I typed other things. Now this will no longer say 10, 10 because it's not thinking the X is 10, it's 5. And the answer is 510. So when we spent $500,000, we got $100,000 out of it. But when we spent $100,000, we got whatever that other number was, which was bigger. But that means, again, we're still making more money, it's just it's slowing down. So now if you maybe make the X 100, or let's go to, let's actually just do 2 numbers. And let's go to 6 and 7. 6 store X. Then recall the function. So we were at 510 originally. Now we're at 658. Let me write these numbers down just for a second. So at X equals 5, F of 5 is 510. Then at X equals 6, F of 6 was, what was that funny number again? I might have to put y'all on pause for a few minutes, just a warning after I finish this example. I got a family thing. Sorry, but it'll just be a few minutes. 658. Now let's do X equals 7. So 7 store X. Recall, recall. Now we're at 794. Let's do the differences of these. So F of 6 minus F of 5, that's the 658 minus the 510, that's 148. Let's do F of 7 minus F of 6. This is the change going from each increment. Again, that's the change, so 794 minus 658. Why is my pen being like that? 790, there we go, 4 minus 658. I think sometimes I'm trying to use my mouse and pen at the same time. And that difference is what, 136. It's a smaller difference, which means the change is decreasing. Again, we're still making more money. You should still arguably keep spending money on advertising because it's going to get you more. But there is a point at which, and you would have to figure this out at a company, at which you decide these diminishing returns are no longer worth you spending more and more and more money. Because if it hits the point where you've got to spend an extra $10 million just to make another $50 in profit, that doesn't seem reasonable. Why would you spend $10 million just to increase your margin by 50 bucks? Because at some point in this function, that would happen. So that's when you say, all right, well, I don't want to do this anymore. And also, as you keep going, eventually you might not be producing efficiently, and all of a sudden you start losing money by spending too much on ads. Maybe you're oversaturating the market and everybody gets sick of seeing your ads, so they don't want to buy your product. I can't tell you how many products I've not bought because I see their ads too much. Although I'm not very easily influenced in terms of advertisements, so I'm a bit of a an outlier in that case, probably. But I really like this problem because it shows that idea of diminishing returns. And again, you're still making another $148,000. You're still making another $136,000 in terms of revenue. You know, there's nothing saying, hey, stop at 5, maybe go to 6, maybe go to 7, maybe go to 8. But you can see that eventually this number is going to keep dropping, and ultimately it might not be worth it to, once again, spend another $10 million just to make $50 in profit. Especially in the real world where these models are not, guaranteed. Maybe you spend that $10 million and something weird happens in the real world and you don't get that extra $50. It ends up costing you $200,000 or something. I don't know. Anything's possible. Let's see. I had another example with something different that was not diminishing returns. I'm going to trim that problem out for time, as we will never finish this course if I do it. That should be it for 3.2. And the family thing I said I might have to pause for, that's they paused for me. So hopefully that doesn't come back up. 3.3, 3.4, excuse me. I say 3, then 4 in type 5. Like I said, we're going to temporarily, if not permanently, skip 3.3. We will come back to it if time is there for it. Optimization, finding absolute maximum and minimum. Values. So up until this point, we've always attached one of two words, relative or local, to these extrema, to these maxes and mins. So remember, relative or local extrema are only max or min in a very small region. There can be multiples of each. When we talk about absolute extrema, the difference here is that we're not looking in just a local region, we're looking at the entire picture. So your absolute max or your absolute min, these are the highest or lowest values of the entire function or restricted window if given. There can only be one of each. There can only be one absolute max and one absolute min. Optimization is all about finding the absolute max and or absolute min. Optimization, there are literally dozens of graduate level mathematics classes on this subject. There are books, not just textbooks, just book after book after book by various authors on optimization. This is one of the most insane fields of mathematics in existence. And it's one of my favorites, besides chaos theory. And I don't even like chaos theory for the pretty pictures that everyone sees. That's awesome and fascinating. I like chaos theory for another reason, but we won't get into that in here because that's not what this course is about. But optimization, I kind of already hinted at this. If you're a business, don't you want to make the most money possible? Don't you want to be producing enough units to make that happen? Because you can make too many, you can make too few. If you make 5 items, maybe your profit's $10. If you make 10 items, maybe your profit's $100. If you make 1,000 items, maybe your profit's $75 because you need a bigger building, or you got too many employees in that building, or you need to redesign the machine that outputs your items because you need to up production by 5,000%, something like that. So you get into these mathematical models that don't just look for a single or the multiple relative extrema, the relative mins or relative maxes, whichever you're interested in. You find all of them and then find which one is the highest or lowest. Okay, so the rant aside, optimization. Finding the absolute max or min. Often, your domain, again, reminder, x values, will be restricted on some bounded interval a to b. We just had a problem with that type of restriction. We didn't actually use anything about it. Let me pull up the section again. I'll bring this back so you can keep writing in a second. No, not 3.1, 3.2. This problem, we said, there it is, that this revenue model was only valid for X values of 0 to 9. So for spending between $0 and $900,000. So this model isn't even going to be good if you use $1 million, anything like that. So some of the numbers I was talking about plugging in, I actually couldn't. But that wasn't necessarily the point. And the good thing is our answer was in that region. But if I got an answer that was outside that region, it wouldn't have been possible and back over there. But this is what I'm referring to in terms of a bounded region. Your X has to be between 0 and 9 or 1 and 5 or whatever numbers it might be. This was written in an inequality form. This is a little more formal and written in interval notation. So this is the same thing as saying A is less than or equal to X is less than or equal to B. They don't have to be bounded. They can be open-ended. They can be parentheses, but I don't like doing that in a business calculus class. It's kind of pointless. For obvious reasons, I think. Why would you want to have the output, the maximum be at a number you can't even use? It wouldn't make sense. So the one thing that differs between local and absolute extrema is that you must plug in all possible how do I want to say this? All possible X values, all potential extrema X values, there we go, into the function to get the outputs, as well as the bounds A and B. From above. So like the 0 and 9 from that very last problem we had, if that was what we were doing. So not only do you have to find the critical numbers, you also have to plug in the boundaries. To the function and see which gives the largest and smallest output. So the basic process is, first step, find f prime of x. Find the first derivative. Second step, find your critical numbers, which is setting the derivative equal to 0 or undefined if it's a rational function. Then evaluate f of x at the critical numbers and the boundary values. The absolute max is the biggest, largest. The absolute min is, guess what, the smallest. Asterisk. You can also use the first and or second derivative test for critical numbers, but you can't do it for the boundaries. So it's kind of not worth it. And I won't do that for any problem that I say find the absolute extrema. Because all it's going to tell you is potential maxes and potential mins. It still doesn't tell you if it is the max or the min unless it's the largest or smallest value. You're still going to have to plug them in, so it's kind of an extraneous step, meaning that it gives you information that would make you maybe feel a little more secure, but it doesn't actually do anything constructive. And there was supposed to be a 3 for the evaluate. So that's your 3-step process. Now, believe it or not, that is pretty much all of the instructions for this section. There's not too much else going on. Yeah, we're good. Okay. I was looking for another piece of paper and I found it. So first derivative test is for local extrema. Second derivative test is for local extrema. When you're talking about absolute extrema, you still need to do a first derivative. You still need to find critical numbers, but you don't have to do test points. You don't have to go to a second derivative and talk about concavity. All you have to do is plug the critical numbers and boundaries into the irregular function, see which one spits out the largest value, see which one spits out the smallest value. That's it. So we can go straight into an example. We may get 2 of these done, we may only get 1 of these done, but we're going to find the absolute extrema for f of x equals x cubed minus 9x squared plus 15x. And we're going to do this on the boundaries of 0 to 3. And I want to talk about this problem if I didn't have the boundaries, because all optimization problems don't have to have boundaries. I don't have to do this. I don't have to say find the extrema on a boundary. I can just say find the absolute extrema on this. And what happens is maybe there's only one of the extrema. Maybe there's only an absolute max. Maybe there's only an absolute min. Maybe there's neither. There are functions that have neither, and I'll demonstrate that after a while. So we're going to find the absolute extrema, and this is bounded. Again, I don't have to give you bounds, but I generally do. I can't think of a test question I'd give you that wasn't bounded. Not for this class. If you're a traditional calculus class, I would. So first, find the first derivative. It's a straight up power rule. I like the power rules for these problems because it makes it easier. 3x squared, just get down to the point, minus, drop the 2 out front, 2 times 9 is 18, decrease the exponent by 1, plus derivative of 15x is 15. We're going to set this equal to 0 to find the critical numbers. So we go 0 equals 3x squared minus 18x plus 15. Then we're going to factor. 0 equals, there's a GCF of 3 to pop out. X squared minus 6x plus 5. Can't take an x because the 15 doesn't have one. Pairs of numbers that multiply to 5 but add to 6 are 1 and 5. So we go 0 equals 3 parentheses. I really like 3 as a GCF, don't I? So we go x1, x5. To make sure they combine to a -6, they both need to be negative. Then we go 0 equals 3, which is trash. X minus 1 equals 0, which means x equals 1. X minus 5 equals 0, which means x equals 5. So our critical numbers are x equals 1 and 5. Now, I need you to notice something, because you can go very, very wrong at this point if you don't notice it. Pay attention to the bounds. We are stuck between 0 and 3. We are only dealing with numbers from 0 to 3, including the ends. 0, 0.9, 1.137, 2.999999999, 3. But we can't use 4. We can't use 7.9. We can't use 12. We can't use -80. Sometimes these critical numbers are outside the bounds, in which case you just throw them out. X equals 5 is not in 0 to 3. So we toss it. Sometimes all the critical numbers are in the bounds. Sometimes none of them are in the bounds. Sometimes one of them or two of them are in the bounds. Guess what? It varies from case to case. All we do now is plug this in to the original function. So we got to plug in the 0, the 1, and the 3 into f of x. The 0 and the 3 were the bounds. The 1 was the critical number that was inside the bounds. So f of 0 is 0 cubed minus 9 times 0 squared plus 15 times 0, which is 0. F of 1 is 1 cubed minus 9 times 1 squared plus 15 times 1, which is 1 minus 9 plus 15, which is 7. And then f of 3 is going to be 3 cubed minus 9 times 3 squared plus 15 times 3. Watch your PEMDAS. 3 cubed is 27. 3 squared is 9. 9 times 9 is 81. So that's minus 81 plus 15 times 3 is 45. So f of 3, what's that? 27. That's negative 9, right? Let me double check that. Let's add the 27 and 45. So that's 52, 62, 72. Yes, negative 9. That is it. That is the entire workload for this problem. In my opinion, absolute extrema are easier to do in our class, not the crazy graduate level optimization problems that I kind of alluded to. We don't do anything like that. In our class, optimization problems, when you're given the function and the bounds, is easier than a first and second derivative test, because you don't have to do test points. You don't have to worry about changing from increasing to decreasing, or changing from concave up to concave down, or just what's the concavity at the test point. All you're looking for is the biggest and the smallest values. So all we're looking at is the 0, the 7, and the negative 9, and finding out which one's biggest and which one's smallest. That's it. Well, 0 is in the middle, 7's the biggest, negative 9's the largest. So f of 1 being 7 produces the max. F of 3 being negative 9 produces the min. So what we can say, I'm going to type it out. The absolute max is 7. Remember, the max or the min is the output, not the input. You've got to get that right. If you get it wrong, that is going to penalize you severely, because it's wrong. The absolute max is the output of 7, and it occurs at x equals 1. The absolute min is the negative 9. It occurs at x equals, what was that, 3? Yes, 3. So in the window of x equals 0 to 3, the largest output occurs at x equals 1, which happened to be a relative extrema too. It would be a relative max if you checked it. But the absolute min is not at a relative extrema, it's at one of the boundaries. There's no way to use the first or second derivative test to check that. It is literally impossible. You just have to plug it in and see which is biggest and which is smallest. Let's pull out our calculator. Let's graph this thing just to see if this agrees. What are we looking at? X cubed minus 9x squared plus 15x, which, by the way, when you're in the graphing section, your x's are not stored as those hard values in the regular screen. Let's zoom standard. So here's our function, and you can see it's got a relative max here, because that's a top of a hill, and there's probably a relative min somewhere about right here if I pulled back on the calculator. Let me just do that. Let's make the, let's say, trace, probably around 5, negative 25. So let's make my window the y minimum negative 30. That might do it. So we can see a peak, we can see a valley. So here's our relative extrema. We got a relative max here, and that relative max occurs at 1. You could prove that with the first derivative test. We didn't actually prove it was a relative max, but we can see it is. Then the relative min occurs right here. What's that look like? About 6, 5? It looks like 5. So the relative min occurs at 5, and it's got a height of negative 25. Now, negative 25 is a smaller value than what occurred at 3. At 3, the output was negative 9. At 5, the output's negative 25. So if we actually were able to have this in the window, that means that this could be the relative, this could be the absolute minimum. But 5, we weren't supposed to be looking at this. We're not even supposed to be looking at this section. We're only supposed to be between 0 and 3. So what I can do is go to the window with the x values, make the x minimum 0, make the x maximum 3, and that way I can only look at the area I'm supposed to look at. And see that relative min is nowhere to be found, so it's definitely not the absolute min. The highest point in this window is right here, and like we said, if you trace it out, it has a height of 7. And the lowest point is over here, right there, when it's x equals 3, and that height is negative 9. Again, with absolute extrema in this course, we tend to be looking at just a small section of the function, not the whole thing. Now, let's go back to this graph, and let's just do a standard zoom. And it's going down on the left, it's going up on the right. You know, maybe make that the y values a little bigger like we had last time. Let's take the y maximum to 50 and the y minimum to negative 50. Just deal with the same x range. This function is going down forever on the left. This function is going up forever on the right. This function, if I didn't bound it between some two values, 0 to 3 or 2 to 1,000,000 or negative 5 to positive 5, if I left this function unbounded, there would be no absolute extrema. I want to actually write that part down. So note, this function was unbounded, meaning we didn't have that 0 to 3 part, there would be no absolute extrema. Because the graph looks like this. Because it goes down forever, there's no min. Because it goes up forever, there's no max. Now, not all polynomials look like that, though. Some polynomials only go down on both ends, so you can have an absolute max on an unbounded polynomial. Some polynomials only go up, and you can have an absolute min on a polynomial as simple as that. But these are just quadratics. We don't deal with just quadratics very often in calculus. We're usually dealing with cubics or worse. So it is possible for a function to not have absolute extrema if it's unbounded. It's possible to only have one of them if it's unbounded. If it's bounded, you're generally going to have both unless it's a horizontal line. That's the only case in which you have no extrema because every output's the same. And I would never do that because it's literally the world's most boring function. I want to make sure that I point out that these are entire functions, not just windows. Let's do one more example. We got just enough time, maybe even a few minutes to spare, but we'll call it after this example. Find the absolute extrema function f of x equals x to the fourth plus 4x cubed plus 15. And we're going to do this on the bounds on the interval -4 to 1. I don't have to give you the bounds written in interval notation. I can give it to you in an inequality form. You have to be able to read both. So same process, because we want the absolute extrema, we don't actually have to do the first or second derivative test. That would only be helpful for identifying relative extrema, and it would do nothing with the bounds. And the relative extrema, if you've got 3 relative maxes, you've got to figure out which one is actually the max, so you got to do the outputs anyways. So don't try and do more. Less is more. First, find the derivative, f prime of x. X to the fourth, bring the 4 down, drop the exponent by 1, plus 4x cubed, bring the 3 out in front and multiply by that 4 to get a 12, decrease the exponent by 1. The derivative of 15 is nothing. Then we find the critical numbers by setting the derivative equal to 0, which can be factored. There's a GCF of 4x squared to take out. When you do that, you'll be left with x minus 3. X plus 3. I don't know why I said minus. I think I was solving the equation in my head. Setting each of those equal to 0, you get 4x squared equals 0 and x plus 3 equals 0. If you remember your pre-calc, you'll know since there's no plus or minuses, this exponent actually has 0 effect on it. But you can divide both sides by 4 to get that x squared equals 0. The only number squared that makes 0 is 0. But you are technically supposed to take the plus or minus square root if you're going to be thorough. And when you do that, you get x equals 0 either way. Subtracting 3 on both sides, not going to show that work. You get x equals -3. These are our critical numbers, 0 and -3. Now, last problem, one of these was not in the interval, but it varies from problem to problem, of course. So we got to think, are 0 and -3 in the interval, or do we need to toss one or toss all of them? 0 is definitely between -4 and 1, and -3 is definitely between -4 and 1. So both are in the bounds. So when we go to plug these into the function, we got to do f of 0, f of -3, f of -4, and f of 1. The order you plug them in does not matter at all. Let's do the critical numbers first. So f of 0, that's an easy one. Again, function, not derivative. 0 to the fourth plus 4 times 0 to the third plus 15. That'll be 15. Let's do the f of, I said I'll do the critical numbers first, so I'll do the f of -3 next. So that's -3 to the fourth power plus 4 times 4 times -3 cubed plus 15, which is positive 81. That's the -3 to the fourth. 3 cubed is 27. That's going to be a negative, though. And 27 times 4, that's 27, 54, 108. And then plus our 15. And then 81 minus 108 plus 15 is -12, right? 107, 27, -27. Yes, good. Then let's do the bounds. F of -4. That's -4 to the fourth power plus 4 times -4 to the third power plus 15. 4 cubed is 64, so times 4 is 256. So that's positive 256 because the negative is evening out. This negative cubed is -64 times 4 is -256. So those are going to cancel. That's nice. Then the plus 15 at the end makes 15. Now what's interesting is f of 0 and f of -4 have the same output, and they're both the largest for now. I'm going to write some asterisks, then I'm going to erase in a second. I'm just saying this number and this number match. and they're both the largest so far. So these are potential maxes. It's possible that the max occurs at two different x values. The absolute max would still be 15. We would just say it occurs at 0 and -4. But we're not done yet. I'm just saying it's possible that happens. We still have one more to do. And that's f of 1, which should be the easiest to do. 1 to the 4th plus 4 times 1 cubed plus 15, which is 1 plus 4 plus 15, which is 20. 20 is the largest, -12 is the smallest. So those are the extrema. So thus we can say the absolute maximum is 20 and occurs at x equals 1. The absolute minimum occurs, sorry, the absolute minimum is -12 and occurs at x equals -3. And there's our answer. So we're going to go ahead and call it a day here. We did finish 3.2, so that homework will be due in a week. And I think I already have that homework set in my math lab. 3.3 we have not finished. We are going to do 2 word problems next class, I believe, in 3.3. And we might do one more of these for practice in 3.3. I don't know, we'll see. And then we'll get into 3.4. I keep forgetting that we're skipping a section. And then we'll go into 3.6. If we finish 3.6 next class, that means the test will be in a week, but I don't know that we're going to yet. I need to pause on that. But for now, hold on. Yes, which is a week from today. So I had given people kind of an extension on 3.1 since we had that whole illness issue, and then me having to do that hour lecture a little late. So yes, 3.1 and 3.2 are due 1 week from today. 3.4 will be due 1 week from next class. 3.6 will depend on when we finish it. And then the test will be a week after finishing 3.6. So for now, we'll call it a day. If you have any questions, please email me. This video will be posted soon, and keep working on the homework, keep working hard. A lot of y'all are doing great with the homework. You did great on the test. So we will keep kicking butt. And yeah, we'll see you Thursday.